Hi, it's Marcel, and welcome to another video. I realized I forgot to really give an introduction. I actually recorded the whole video already. This is spoilers. I don't know how to make the spoilers go away. Let's make a new page. Okay, so there are no spoilers. I thought like I should actually make an introduction to the Fourier uncertainty principle and like sort of why it's interesting, because in the previous take, which is actually you're gonna see it in like a minute or two, I just like dive straight into the math and don't tell you at all what we're even talking about. Now the problem is I don't really know too much about like physics and stuff, and really Fourier uncertainty is kind of maybe you've heard of like uncertainty principles, like with signals and stuff. Like you can't, or the Heisenberg uncertainty principle, like you can't know the position and momentum of a particle. I don't really know that stuff so well, but there's a really good video by 3 Blue 1 Brown on this principle, and you'll see kind of in that video if you watch it, like there are sort of pictures like this where you get some function f, and maybe it looks like this, and I don't know, it looks like that, okay? And then you get f bar, okay, I don't really know. There's like waves and stuff. And then you get f bar, and you can't have, well, that kind of tells you like the frequencies or something, you know? I don't want to speak too much about physics because I'll mess it all up, but the idea is you can't have like certainty about f, like where it's concentrated, and f bar, okay? So either the support, I just realized this is a really stupid picture, but you'll see what I mean later in the discrete case, but you could also watch 3 Blue 1 Brown's video on the uncertainty principle in the general case, and like it shows up in physics a lot, and that's really cool, but it's really just an instance of the Fourier uncertainty principle happening over and over and over in physics. So this video will just be about the math. It'll just be in the discrete case, and it'll actually set up. So in this first video, there's only going to be the introduction and sort of what is a function on an abelian group, what is a character, what is the Fourier transform of a function, and then I'll give examples of 3 functions and their Fourier transforms. Like they're going to be really tiny functions on like small abelian groups, and then their Fourier transforms, and then we'll see this little like phenomenon arise, and then I'll state the uncertainty principle, which we won't prove in this video, but will be proved in the one after this, which will be up at some point, hopefully like tomorrow or the day after, or the day after that, whenever I decide to get to it. Okay, so now I'm going to go to the original start of the video, and also I apologize for the audio. It kind of cuts out whenever I mumble a bit. I think there's some software that does some correction, but if I speak too quietly, it like cuts out completely, and I hope it's not too annoying. It is pretty comprehensible. It's just a little like weird sometimes. Okay, enjoy. And welcome to this video about the Fourier uncertainty principle on finite abelian groups. Okay, so let's get started. All right, so we are going to be working with finite abelian groups, so let Z be a finite, there's an I somewhere in there, abelian group. The character on Z is a homomorphism from Z to the multiplicative group of complex numbers, well, minus 0, because if you have 0, then it's not a group. Okay, and so since it's a homomorphism from this finite group Z to C star, we have that. So if chi is a character, so chi goes from from Z to the complex numbers, then chi of x has to be, the norm has to be equal to 1 for all x in z. Now, why is that? Well, it's because it's a homomorphism, right? So if we take the identity element, it's got to go to 1, because that's the identity of the multiplicative group of complex, of non-zero complex numbers. But in a finite group, every group element, if you take it to the power, the size of the group, say, some power, it'll equal 1. So you have to have it so that in complex numbers, you take whatever chi of x is, and you take it to some power, and it's going to be equal to 1. Well, you can't have if the norm doesn't equal 1, then that's not. Okay, so really, you can think of a character not just as a homomorphism from z to the complex numbers, it's actually a homomorphism to the unit circle. Okay, now the set of all characters, forms a group, okay, which we will denote, which here? We will denote by z hat. Okay. Also, my writing, as you can see, is very messy. So as always, I'm going to put some notes in the description that you can read in case. I'm also going to try to say everything that I write, so that'll help. But if you really can't read this, really bothers you, there are notes you can follow. Okay. Now, where am I? Okay, so now, if z equals, okay, it's a direct sum of n1 of this is I'm writing this for z mod n1 z. So zn2 all the way up to z and r. This is just the fundamental theorem of finite abelian groups, right? So you can take your finite abelian group and it's a direct sum of or direct product of cyclic groups. Now, if you write like that, then for every u, which is u1 up to ur in z, okay, so we identify this element u of z with a tuple of elements in these cyclic groups. The function chi of u from z to c, given by chi of u x1 up to xr is equal to the product of x1 to r of e to the 2 pi I ui xi over ni. Okay, this is a homomorphism. Okay, so e to these are on the unit circle, right? So e to the pi I, 2 pi I times this number ui xi over ni. That's how far on the circle we go. Pi i's all the way around, obviously. Okay, so this is a homomorphism from z to the complex numbers, to the unit circle. Okay, and that's a character. Given by that is a character. And in fact, the map u goes to chi u is an isomorphism. Isomorphism of groups from FROM z to z hat. Sorry, I haven't made a video for a very long time, and I'm dealing with this writing thingamajig. Okay, so now, okay, so the space of functions from Z to C can be equipped with an inner product. Okay, by setting, okay, we need to know an inner product takes two elements, two functions, f and g, and we want to kind of figure out like the sort of, it's like a dot product, right, between these functions. And we're going to define it like this: the expectation of all x over z of f of x, g of x, bar. Okay, this bar is a complex conjugate. Okay, and what is the expectation? Sorry. So what expectation x in z of some function f of x, big F, is just 1 over the size of z, it's the average, of the sum x in z of f of x. Okay, so we take the expectation. Let's get a new page. How do I get a new page? That's interesting. Oh, I did it. Okay. So the space of functions can be equipped with inner product. So we have an inner product space, and actually, the space of functions from the dual group to the complex numbers can also be equipped with an inner product. Let's figure that out. Sorry, the space from z hat to the complex numbers can also be into an inner product space by setting, we're going to write f hat, g hat. These are functions that take characters. And instead of the average this time, we take the sum. So all chi in z hat, but the same thing, f hat of chi, g hat of chi. Okay. Now, this is a video about Fourier analysis. So we're gonna define now the Fourier transform. Okay, so you might have seen this before. So for f from z to c, we define the Fourier transform of f to be the function so we're given f. The function looks like this. It's a member of the space of all functions from z hat to c, so it takes characters. And how does it define? So f hat of chi is equal to, we inner product f with chi. Okay, and well, what is that? It's the expectation of all x and z of f of x chi of x bar. Okay, so that's the Fourier transform. So kind of like why? Okay, hang on, just give me 1 second. Let's one more little note. So we can associate to any alpha in z the character chi of alpha, right? So we saw there's an isomorphism of groups with that formula with e to the something, right? So we can write f hat of alpha, and we're not going to be pedantic about that. That really means f hat of chi alpha, because f hat takes characters, and this is the Fourier coefficient of f at alpha. I guess this is a definition. Okay, and like, in fact, we'll see in the next video. I don't want to get into like all the theorems until the next video, but in this video we're going to just get some definitions out of the way, and then we are going to see some examples of functions f and their Fourier transforms. Okay, and then you're gonna kind of see this sort of phenomenon that we're gonna call the uncertainty principle, and then in the next video we'll prove that, and then maybe I'll even make them into a longer series. There are better Fourier uncertainty principles for certain groups, cyclic groups, and we'll try and prove that. But that'll take us on like a really long path. I don't know if I'll make all those videos, but we'll at least start here. Okay. So I mean, but kind of glimpsing ahead, you'll see that there's this formula that says we can write f of x as a sum of alpha in z, f hat of alpha, chi alpha of, am I writing this? Chi alpha of x? Yes. Okay, I hope I didn't get this formula wrong. But what that means is really, okay, so there's the space of functions from z to c is a vector space of dimension size of z, right? And these are the basis elements. So really, f is as a function can be written as a linear combination of characters, and the coefficients in this linear combination are exactly the Fourier coefficients of f hat alpha. So that's what's important. This is called the Fourier inversion formula. Anyway, we're not going to dwell too much on that at the moment. Okay, we're just going to talk about some examples. So the Fourier transform. Okay, so I'm going to give like 3 examples, and they're all going to be really simple, but it'll sort of, honestly, I've seen the definition of Fourier transform like a million times in like undergrad classes, and honestly, until like today when I sat down and did a bunch of examples, like do I finally kind of you have to do examples, and sometimes it's easy to just not do them because in class you learn like definitions and you're like and theorems and stuff, and you can totally prove things and use the definitions, but sometimes it's nice to like spend honestly 15 minutes and just work with some examples. So we'll do that. If you really hate examples, like get out of here with examples, I only want theorems, then you can skip to the next video, which I'll make like tomorrow. Examples. Okay. So let's make a function f from let's take the cyclic group as Z3 to C. It's like the smallest group I can think of. Okay, so X. Okay, so there's 3 elements in Z3. There's 0, there's 1, and there's 2. All right. And let's make f the simplest function I can think of, which is just the constant function 1. Okay, now what's f hat? Okay, let's try to figure it out. Well, chi of 0, okay, is so we're taking the identity of the group Z3, and we are sending it to the group of characters. So it really ought to be the identity character, right? So in fact it is. So chi 0 of x is equal to 1 for all x. Okay, so so let's do this. So f hat of 0 is this expectation. It's x and z. F of x chi 0 of x bar. Okay, so this is an expectation, so it's going to be a third times some sum, right? So f of 1 times 1. 1 bar is 1, right? Plus f of 2 plus f of 3. Okay, and what's that? This is f of 1 is just 1, f of 2 is just 2. I'm sorry, f of 1 is just 1, f of 2 is 1, and f of 3 is 1. So this is 3 in here, and it's divided by 3, so it's 1. Oof, that was hard. Okay, so we find that f hat of 0 is 1. All right, now let's go on to the next one. What does chi of 1 look like? Oh, sorry, chi sub 1. Well, by the formula, we have this, right? So this is just a cyclic group, so there's like some product, but we just have a cyclic group. So chi 1 of x is e to the 2 pi I x times 1, which I'm not going to write, over 3. Okay, and if we draw a little unit circle here, this is the complex plane. this is a circle. It's the best one I can draw. And let's do colors. I'm gonna draw little points here in red. I hope you can see red. If you can't, I hope you can at least see the dots. Oops, oopsie. Okay. So this is omega. No, this is not omega. Well, it's omega to the 3, which is 1. And this is omega, and this is omega squared. Okay? And omega is e to the 2 pi I over 3. Does that make sense? All right. So chi1 of x is equal to omega to the power x. Okay? All right, so let's figure that out. So f hat of 1 is equal to expectation of x and z, f of x, chi1 of x bar. Okay, so that's a third times a sum. Okay, so f of everything is just 1, so I'm not going to write that. But we have omega to the 0 bar plus omega bar plus omega squared bar. Okay, and now omega bar is actually omega squared, because you can see just reflect over the x-axis, and omega squared bar is omega, so whatever. We're just summing it in a different order. But actually, what does omega plus omega squared, I'm like, okay, let's try and draw this correctly. So I didn't draw this very well, but this is actually a 60-degree angle. Okay, 60 degrees. So the real part of omega is cos of 60, which is half, I hope. And so if you add omega and omega squared, you get -1. So omega plus omega squared is -1. And since omega 0 is 1, this is actually just 0. Okay, so we find that f hat of 1 is 0. And now chi2 of x, okay, you can maybe guess what is going to happen here, but it's e to the 4 pi I x over 3. And so that's just omega to the 2x. And then when you do this whole sum, you're going to get a third times omega to the 0, same thing, bar plus omega squared bar plus omega to the 4, which is the same as omega bar. So it's the same sum, just in a different order, and it's also equal to 0. Okay? So we've done this example in Z3. We took a constant function 1, and we found that the Fourier transform at each of the coefficients or at each of the elements of Z looks like this. It's 1 at 0, and it's 0 everywhere else. It's kind of interesting. Okay? We're going to do 2 more examples, and as soon as you get tired of the examples, you can switch it off. Nobody is going to make you finish all of them, but I think it's good to learn what the Fourier transform is, and it will hint. Actually, don't just switch off the video. I'll put a little timestamp so you can skip ahead, so we can talk about the Fourier uncertainty principle, which is like setting up the next video. So let's just do this example. So now f goes from, what's the next biggest group? The cyclic group on 4 elements, to C. Okay. We're going to do the exact same thing. Okay. Lines are hard. X. There are now 4 different x's. F. Okay, what did I choose? Let's make it this function. 0, 1, 0, 1. Okay? So it's 0 on 0 and 2, and it's 1 on 1 and 3. Okay, all my functions are Boolean functions because I don't want to do any computation that's harder than that. Okay, let's figure out f hat. So again, chi0 of x is the identity. Okay, so f hat of 0 is equal to expectation of x and z, f hat of x, or f of x, chi0 of x bar, but it's just 1. So that's a quarter, and a quarter of it's just 1 and 3 that we have to worry about, right? So f of 1 plus f of 3, which is if this is equal to 1, that's equal to 1. So it's just 2 over 4. That's a quarter. Okay? Sorry, it's a half. It's 2 quarters. Okay? Math is really difficult. Now f hat of 1, okay, it gets a little more dicey. Well, to figure out f hat of 1, we need to know what chi 1 is. So chi 1 of x is equal to e to the 2 pi I x over 4, okay? Now that's actually equal to e to the pi I x over 2, or since e to the pi I over 2, e to the pi I is negative 1. E to the pi over 2 is the square root of negative 1, and the square root of negative 1 is I. And so it's I to the x. Okay, so let's draw a little picture of what this looks like. I did the colors last time, so let's pick a different color. I hope that you can see green. Green is going to be the color this time. So this is my complex plane. And this is 1, this is I squared, and this is I cubed. And I cubed, I to the 4 is 1. Okay, so chi 1 of x is I to the x. And so f hat of 1 is, let's not write the whole thing again. It's going to be a quarter, okay, of chi 1 of 1 bar plus chi 1 of 3 bar, which is equal to a quarter I bar plus I cubed bar. Now what is that? Well, I bar is I cubed, and I cubed bar is I. But if you add them together, I mean, look at I and I cubed, you add them together, you're going to get 0. They're inverses of each other. So this is actually equal to 0. Okay, so we found that f hat of 1 is 0. That's kind of interesting. Okay, now let's kind of skip forward a bit. So chi 2 of x is equal to e to the 4 pi I x over 4 is equal to e to the pi, or the I pi x, which is negative 1 to the x. Okay, and now if we do this out, okay, we can negative 1 to the 1 plus negative 1 to the 3. But what is that? So this is just negative 1, and this is also just negative 1. So it's negative 2 over 2, which is, this should be over 4, sorry. So it's negative 2 over 4, which is negative a half. Okay, so this is negative a half. And chi 3 is just going to be the same as chi 1. Well, not really, but I don't want to do the whole thing again. You're going to get the sum, but it's going to be in the opposite order. It's going to be, you know what? I'll just write it. Chi 3 of x. I'm not going to write chi 3 of x, but I'm going to write f hat. F hat of 3 is going to be a quarter of I cubed bar plus I to the 9 bar. But I to the 9 is I, and the bar, so it's cubed. It's equal to a quarter I cubed bar is just I, and I bar is I cubed, which is also 0. Okay? Okay, so we found that this function, which is 0 on the even numbers, and then 1 on the odd numbers, and I don't even know if there's even an odd in cyclic group, but whatever. This is, you get f hat, which is 0 on like less of, it's like, it's not quite like this one where it was like 0 everywhere except for on the identity, but it's still kind of, like it still has holes in it. Okay, so maybe that's leading towards something. I don't know. Okay, we're gonna do one more example. So this last example goes from z to the 5, obviously, because what comes after 3 and 4 is 5. Whatever, it's on the next page. Okay. Oh yes, okay, so this time the table looks like this. Hang on, x goes on top, right? X, f bar. So there are 5 elements in Z5, Okay, and the function is going to be 0, 0, 1, 0, 0. Okay? Now, chi 0 of x is just 1. Chi 1 of x is going to be omega to the x. Chi 2 of x is going to be omega to 2x. And chi 3 of x to 3x. 4 of x equals omega to the 4x. Now, what is omega? Okay. As you expect, it is on the unit circle. Let's pick, what did we do? We did red and green. Let's pick blue. And blue, okay, so I'm going to try to do this in some amount of like geometrically correct. That's 5, that's a pentagon. Okay. This is 1, this is omega, so omega squared, omega cubed, and omega to the 4. And then omega to the 5 is just 1. Okay, and now here we only have to worry about f2, right? So because f of everything else is 0. So f hat of 0 is a fifth times f2, which is 1, chi 0 of 2, which is just a fifth. Okay, so that's easy. F hat of 1 is a fifth times chi 1 of 2, which is a fifth times, I guess it's bar. So that's omega squared bar. So omega squared bar is omega cubed. So it's a fifth of omega cubed. Okay, so that's omega cubed. F hat of 2 is a fifth times omega, so it's going to be f hat of 2. So omega to the 2 times 2, which is omega to the 4, then bar, so that's omega. So that's omega. F hat of 3 is a fifth times omega to the 3 times 2, which is 6, and that's the same as omega, but then omega bar is omega to the 4. Okay, so it's a fifth. This is over 5. This is over 5, and this is omega to the 4 over 5. And what's the last one? The last one has to be omega squared over 5, right? Because in math, if you see like a pattern, look, we haven't used 5 yet. I mean, sorry, we haven't used 2 yet. So if you look, we used omega to the 5, omega to the 3, omega to the 4. We haven't used 2 yet, so that's the answer. Okay, but that's interesting. Look, when we had an f that had like 1s everywhere, we had a Fourier transform that had lots of 0s everywhere. When we have an f that has like 2, like half of it is filled, the Fourier transform is also like half filled. And when we have a f that is like just a point, sort of like the characteristic function of a point, now we have the Fourier transform that's like full support. Okay, and I use the word support, which we're going to define like right now. Also, like I picked examples that make this exact, but I'm going to get to what the theorem actually says. Okay, so another definition. The support of a function f from z to complex number, z is an abelian group, finite abelian group, is this set. So it's a set of all x and z such that f of x is not equal to 0. Okay? Support. We write kind of like a norm of f, but the 0th norm to be the size of the support of f. So I'll put the brackets, okay? And the same definitions if f goes from z hat to complex numbers, whatever, you can figure that out. And so it seems from our examples that we can't have f being both the support of f to be small and the support of f hat to be small. Okay? So I didn't make any examples of this, but it is possible for you to get like a full support in f and a full support in f hat. That's okay. But you can't have like a small support in f and a small support in f hat. And if you look, actually, okay, so the support of f here is 3. It has 3 elements. And the support of f hat here has one element. And if you take 3 times 1, you get 3. So that's interesting. And here it's 2 times 2, and that's equal to 4, which is the size of the group. And this is 1 times 5, and 5 was the size of the group. So the theorem, which we'll actually prove in the next video, is that this is called the Fourier uncertainty principle. That's the following. So let Z be a finite abelian group and Z hat be its dual. Okay, if f is a function from z to the complex numbers that is not identically 0, then I guess, and okay, let's just write this. Then f, the size of the support of f times the size of the support of f hat is at least the size of the group. Okay, where f hat is the Fourier transform of f. Okay, so the 3 examples that we gave above are when this is actually tight, right? We saw that the support of f, the size of the supports, actually multiplied to the size of the group. And you can also prove that this happens exactly when the f is some multiple of the characteristic function of a coset. Okay, so if you notice here, this is a coset. Well, it's just sorry, the coset of some subgroup. So this is just the subgroup, the identity subgroup, but it's shifted by 2. And this was the subgroup z squared. I'm sorry, z mod 2z, but shifted by 1. And then this is the subgroup, the whole group, shifted by, I don't know, you can decide what it's shifted by. And yes, we got that it's tight. So we're not going to prove that though. Next episode, we're going to prove that this version, just the bound, okay? And to do that, we'll need some basic tools from Fourier analysis, like Parseval's theorem, the Fourier inversion formula, I think maybe Cauchy-Schwarz. And I'll try to make this complete as possible. Maybe we'll skip some of the proofs, maybe we won't. I think the proofs are small, so. Anyway, that's the next video. I hope this was mildly interesting. If you sat through all the examples, then you are a very good viewer. Okay, see you next time. Go outside and play.